And I would like to show first this exercise here. There is about 3 electric charges that are arranged found below. So let me just only recall quickly something about the uh, electric charge. So remember that when you have 2 positive charges, the force of in this case, the force between these 2 positive charges here, the electric force between these 2 positive charges, will be a repulsive force, a force of repulsion, and repel each other. Of course, these 2 charges we have, some magnitude, right? So let's say that this one is the charge Q1, and this is the charge Q2, and let's say that these 2 charges are at the distance R or D, one from the other. So this force that you see here is the force that the charge 2 exerts on the charge 1, and this will be the force that the charge 1 exerts on the charge 2. And if we want to calculate the magnitude of force, because these 2 forces have the same magnitude, the magnitude of force is K, that is the Coulomb constant, times Q sub 1, Q sub 2 over the square of the distance. We can use the absolute values of Q sub 1 and Q sub 2. Like that, we don't worry about the signs of the charge in terms of finding the magnitude of the force. Now, when the forces have different signs, when the charges have different signs, then the forces here are going to be forces of attraction. So we have, again, this is the, I said different signs, so we'll change the signs. This one is negative. So this is the charge Q1, this is the charge Q2, and this is the distance R between the charges. Now we have the force of attraction. This one is the force that 2 exerts on 1, and this is the force that 1 exerts on 2. And the expression to calculate the force is the same. The expression doesn't change. Remember, I said you can use the absolute values, so you can write the expression also like force equals A times the absolute value of Q sub 1, the absolute value of Q sub 2, square distance. So this is something that is important to understand in order to solve this exercise effectively. So let's then go over the exercise now that we want to solve. We erase this quickly to have enough space to solve this exercise. So they say 3 charges are arranged as shown below. Find the magnitude and direction of the electrostatic force on the charge that is at the origin. So basically, we want to find, the force acting on the charge of 5 nanocoulombs. The charge of 5 nanocoulombs. So let's analyze quickly the direction of the forces that are acting on the charge. So due to the positive charge of 6 nanocoulomb, to the action of positive charge of 6 nanocoulombs on this positive charge of 5 nanocoulombs, there would be a force of propulsion, so pointing in this direction, pointing left, acting on the charge of 5 nanocoulombs. If I say that this charge will be Q sub 1, and this one will be Q sub 2, and then this one, the negative charge, is Q sub 3. The force in red, that I am representing here, that is a repulsive force, is the force that 2 hurts on 1. Now, due to the action of the charge of negative 3 nanocoulombs on the charge of 5 nanocoulombs, so due to the action of Q sub 3 on Q sub 1, there would be a force that would be an attractive force, that is going to try to pull Q sub 1 toward Q sub 3, right? So we have one force here, it is a force of attraction. That is the force that 3 hertz on 1. So basically, I can just take the charge Q sub 1 out. And then I can represent the forces F21 and F31 on it. Right? And then we have that there would be here this force that is F21 for the 2 hertz on 1. We don't know its magnitude yet. Where we have this force that 3 hertz on 1. I did the calculation, so I know this force would be larger than the force of 2 hertz on 1. So this would be the force that 3 hertz on 1. And then graphically, using the method of the parallelogram, we can find the resultant force on the particle 1, from charge 1 to charge 2 and 3. And that resultant force would be a force like this. Okay, and this would be its magnitude. Let us call this force on particle 1. And the angle that the force makes with respect to the negative y-axis, I will call that angle θ. So what I want to do in this problem, I want to find the magnitude of the force F sub 1 and the angle that the force F sub 1 makes with respect to the negative y-axis. So let's then start just, of course, with the calculations. In this case, we're going to be using the superposition principle. So I would say that the force that 2 hertz on 1 is equals the Coulomb constant times absolute value of Q sub 1, absolute value 1 is equals the Coulomb constant times absolute value of Q sub 1, absolute value of Q sub 2 over the distance from 1 to 2 squared So it would be 8.99 times 10 to the 9 newtons meter squared over Coulomb square. That is K times. I'm going to find the absolute values anyway. Q1 and Q2 are positive. The absolute value for positive number is positive. So I have 5 nanocoulombs, that is Q 1 nano is 10 to the negative 9. So it would be 5.00 times 10 to the negative 9 coulombs. Because I have to convert the nanocoulombs into coulombs. And then also I have 6.00 times 10 to the negative 9 coulombs. And all this is divided by the distance from charge to charge, 30.300 meters squared. So when you calculate this force at 2 hertz on 1, we get that the magnitude here is 2,996.7 times 10 to the negative 9 newtons. So we can write this in scientific notation. So we can say that this is 2.99 times 10 to the negative 6 newtons. So we can round it to 3.00 times 10 to the negative 6 newtons. Now I'm going to find the force at 3 hertz on 1. And the force at 3 hertz on 1 is K times the absolute value of Q sub 1, absolute value of Q sub 3 over the distance from 1 to 3 squared. K is 8.99 times 10 to the 9 Newton meters squared per Coulomb square. Q sub 1 absolute value of Q sub 1 is absolute value of 5 nanocoulombs, so it's 5.00 times 10 to the negative 9 coulombs. Absolute value of negative 3 nanocoulombs will be positive 3 nanocoulombs, so it will be positive 3.00 times 10 to the negative 9 coulombs. And the distance from 1 to 3 is 0.100 meters, so we divide by 0.100 meters squared. So we get that the force at 3 hertz on 1, you know, in this case is approximately 13,485 times 10 to the negative 9 newtons. So we can write this with the same power of 10 that I have my force at 2 hertz on 1, so I can combine easier development forces later. So if we say that regarding that is not going to be scientific notation, it's not going to be now approximately 13.5 times 10 to the negative 6 newtons. And then I didn't write it, okay, 1.35 times 10 to the negative 5 because I want to have the same power of 10, 10 to the negative 6, you know, for these two forces. Now, using superposition principle, right? I can say now that the square of the force 1 is equal to the square of the force at 2 hertz on 1 plus the square of the force at 3 hertz on 1. So I can now solve for the force of particle 1, and that is the square root of the square that the force 2 hertz on force 1 square plus the square that the force that particle 3 hertz on particle 1 square. So this would be the square root of 3.00 times 10 to the negative 6 newtons squared plus, then we have 13.5 times 10 to the negative 6 newtons. Then we have 13.5 times 10 to the negative 6 newtons squared. And when we calculate that, we're going to get that this force is 1.38 times 10 to the negative 5 newtons. There's no reason scientific notation. So that would be the magnitude of the force F1. So this 1.38 times 10 to the negative 5 newtons is this force F1. That is the resultant force acting on the particle. Now, we don't know yet what is the angle, so the direction of the force. So I will find the angle with respect to the negative y-axis. So let me say that zeta, and this is an expression that you can always use, is the tangent inverse of the force acting in the y direction over the force acting in the x direction. So tangent inverse of the force at 3 megahertz on 1 over the force at 2 megahertz on 1. So zeta would be the tangent inverse of, in this case, 13.5 times 10 to the negative 6 newtons divided by 3.00 times 10 to the negative 6 newtons. Of course, 10 to the negative 6 newton, 10 to the negative 6 newton cancel out, and then you get zeta is the tangent inverse of 13.5 over 3.00, and then zeta would be approximately 77.47 degree, which is approximately equal to 77.5 degree. 77.5 degree below the negative x-axis. Below the negative x-axis, because you must explain with respect to what axis is just the 77.5 degree that you're measuring, right? So we say, okay, I'm measuring this with respect to the negative x-axis, right? This axis over here. So it's 77.5 degree below that negative x-axis. So this is a problem about the interaction between three electric charges, and we can calculate the electrostatic force, the force on one of the charges to the action of the other two. We can calculate not only the magnitude of that force, but we can also calculate the angle or the direction of the force, of course. Let me see another problem that I have for you here. This problem is pretty easy, but it's very interesting. We have a small object of mass 3.80 grams and with a negative charge of negative 18.0 microcoulomb. This object is suspended motionless above the ground when it's immersed in a uniform electric field perpendicular to the ground. So what is the magnitude and direction of this electric field? This is a super interesting exercise. It's very easy, but it's interesting. So we have here the ground, and then we have an electric field that is perpendicular to the ground. These are the electric lines, right? It's a constant electric field. Now, what we don't know is the intensity of this electric field. So we have had to find the intensity and the magnitude of this electric field, but also its direction. Now, what happens? The charge that we have is negative. Because it's a charge Q with mass M. So Q is minus 18.0 microcoulomb, and the mass M is 3.8 grams. Now let me explain you something. This charge is above the ground. This particle, this object, this mass is above the ground. It's like suspended. It's not moving, it's not falling, it's not moving up, it's just suspended, like levitation. So what happens here? You know that there is a force that is the gravity acting like this. Under the action of the force of gravity only, this body have to fall toward the ground. So if this body is just suspended above the ground and motionless, is because there should be another force that is counteracting the effect of the force of gravity. And what could be that other force counteracting the effect of the force of gravity? The electric force. So we need an electric force to just be acting over here with the same magnitude of the force of gravity, but with opposite direction. Now, what happened with the forces and the electric fields is this. We know that the vector electric field is equal to force divided by the particle, or the charge of the particle, the charge of the particle. When Q is positive, the electric field vector and the force vector have the same direction. These apply to positive particles. But when Q charge is negative, the electric field vector and the force vector have opposite directions. So that means I have a negative particle here, and I have a force that. So that means I have a negative particle here, and I have a force that points outward. That is the electric force that needs to balance the force of gravity. So I have no choice other than an electric field that points downward, points toward the ground, because this is the only way that the electric force can point downward for this negative particle, and that the electric force will be counteracting the action of the force of gravity. So now I know the direction of the electric field. The electric field points downward. The explanation is just that. Now, what I know, if I make a sum of the forces in Y, since this particle is suspended, tensor of forces in y needs to be 0 because the particle is not accelerated in either direction, up or down. So taking positive, the force is pointing up. I would say that, the electric force minus the force of gravity is equal to 0. So we can say that the electric force is going to be equal to the force of gravity. Now we know that this electric force, if we said that electric field is force over particle, the charge of the particle, then the force would be the field times the charge of the particle. So we'll substitute this electric force by electric field times the particle charge. And I will substitute the force of gravity by mass gravity. What I want to do is to calculate the electric field. So we just solve for the electric field. We say that the electric field is mass gravity divided by the charge of the particle, of the charge of the body. So now we get that E is equals to, what is the mass here? 3.80 grams. I remember that 3.80 grams times 1 kilogram over 1,000 grams, it becomes 3.80 times 10 to the negative 3 kilograms, right? This would be 3.80 times 10 to the negative 3 kilograms. So I have to use the mass in kilograms. So 3.80 times 10 to the negative 3 kilograms times the gravity, 9.80 meters per second squared, divided by Q, that is 18 microcoulombs, negative 18 microcoulombs, but the negative, just let me make analysis of the directions of the electric field force. So I will just take the absolute value of the charge of the particle, which is 18.0 microcoulombs. So micro is 10 to the negative 6. So this is 18.0 times 10 to the negative 6 coulombs. Times 10 to the negative 6 coulombs. And when we calculate the values here, we're going to get that the value is 2.07 times 10 to the third newtons per coulomb. The units of electric field are newtons per coulomb. So now we know that we have an electric field vector of 2.07 times 10 to the third newtons per coulomb downward, which is perpendicular to the ground, and of course pointing downward because it's the only way that the electric force can point up to counteract the first effect of the force of the ground. So this should be in this case just downwards. So this is just the magnitude and direction of the electric field, the magnitude and direction of the electric field. There is here another exercise that I find also very interesting. And it's the exercise 23. It's going to be the last exercise we explain about this part, about this topic 15. Sorry, yeah, 15. And look at this exercise. They say A proton accelerates from rest in a uniform electric field of 640 newtons per coulomb. At some later time, its speed is 1.20 times 10 to the 6 meters per second. Find the magnitude of the acceleration of the proton. How long does it take the proton to reach this speed? How far has it moved in that interval? What is its kinetic energy at the later time? So let's assume that this electric field is pointing to the right, like this. It's a uniform electric field, and we're going to be taking that is pointing right. So I have a proton. A proton is a positive charge. So I have my proton over here. So due to the action of the electric field, there will be a force in this proton that is going to be in the same direction as the electric field. So this is the force of the proton due to the action of the electric field. Due to the action of this force, then the proton will be moving with acceleration to the right. And eventually the proton will be in this other position. What we know is that in this position, the speed of the proton, where we're going to call final speed of the proton, would be 1.20 times 10 to the 6 meters per second. We know that the speed of the proton at this other position, so its initial speed, it was accelerating from rest to 0.00 meters per second. And we know the intensity of the electric field, that is 640. And we know the intensity of the electric field, that is 640 newtons per coulomb. So the first that they want to calculate is just the acceleration of the proton. So I will go to the second Newton's law, and I will remind you that the acceleration is equal to the quotient between the force acting on the body divided by the mass of the body. So if what I have is a proton, we say that the acceleration in the proton, the acceleration of the proton, will be equal to the electric force divided by the mass of the proton. Now, the electric force acting on this proton will be equal to the intensity of the field times the charge of the proton, and divided by the mass of the proton. So we know the intensity of the field, so the acceleration of this proton is the intensity of the field, 640 Newton per coulomb, times the charge of the proton is the same as the charge of the electron, but positive, so it's 1.60 times 10 to the negative 19 coulombs, divided by the mass of the proton. Is also a data you can find in the book, you can find in the internet, which is approximately 1.67 times 10 to the negative 27 kilograms. Negative 27 kilograms. So when you perform these operations, we get that the acceleration of the proton is approximately 6.13 times 10 to the 10. meters per second squared. This would be the acceleration of the proton. Now, why is it important to find the acceleration? Well, first they are asking about what is the acceleration, but also because now I have to find how long does it take for the proton to reach its speed. So how long take, so what is the time that take this proton to reach this speed of 1.20 times 10 to the 6 meters per second if the acceleration of the proton would be 6.3 times 10 to the 10 meters per second squared. And then we have to go and take the equations of the kinematics again. That's why I just made that emphasis in kinematics. Because we said that okay, I know the final velocity, I know the initial velocity, I know the acceleration, I want to find the time. So we say that the final velocity is equal to the initial velocity plus acceleration time. This initial velocity is 0 because the proton is initially at rest. So now I know that this f, the final velocity, the velocity at this point is equal to acceleration time. So if I want to find the time, I will divide by the acceleration of the proton, and this will be equal to the time. So if I divide the velocity of the proton at this point, 1.20 times 10 to the 6 meters per second, and I divide that by the acceleration of the proton, that is 6.13 times 10 to the 10 meters per second squared. I say, well, this will be the time. You can calculate the time, and you will get that the time would be, it would be 1.96 times 10 to the negative 5 seconds, which is going to be the same that 19.6 times 10 to the negative 6 seconds, and 10 to the negative 6 seconds is a microsecond, so it's going to be 19.6 microseconds. So the time that takes, for the proton to go from that speed 0 to speed 1.20 times 10 to the 6 meters per second when the proton is released in this electric field is 19.6 meters per second. Sorry, 19.6 microseconds. The next they ask you is how far has it moved in that interval. So again, we're going to use an equation of kinematics. In this case, I will use that equation to say that delta x is equals to sub 0 t minus 1 over 2 at squared. We know that the initial speed of the proton was 0, so I know that delta x, how far it moves, how far it goes, is 1 over 2 at squared. We know the acceleration, we know the time, so delta x will be 1 over 2. The acceleration, there is 6.13 times 10 to the 10 meters per second squared times the time. That is 19.6 times 10 to the negative 6 seconds. So delta x would be, when you calculate this and just, work with the powers of 10 you get, you will get here that this is approximately 11.8 meters. So how far it goes? 11.8 meters. The next that they ask you, the last, is what is the kinetic energy at the later time? What is the kinetic energy at the later time? So what is the kinetic energy here at this point? Well, the kinetic energy of the proton will be equal to 1 over 2 the mass of the proton times the square of the final velocity. So the kinetic energy of the proton at this point, here, when you have a speed of 1.10 times 6 meters per second, it's going to be 1 over 2 the mass of the proton, that is 1.67 times 10 to the negative 27, and use this a little bit to the left. So the kinetic energy of the proton would be 1 over 2 the mass of the proton. We know that it's 1.67 times 10 to the negative 27 kilograms. Times the square of the speed of the proton. There is 1.20 times 10 to the 6 meters per second squared. So the kinetic energy of the proton in this case would be, when you calculate that, 1.20 times 10 to the negative 15 joules. So here we found then the kinetic energy.